Swayam Prabha. Digital India. Educated India.
Good morning. So in this lecture, I'll be talking about drying operations. So among all the other mass transfer operations, drying perhaps is the most complicated operation in terms of how we approach, how we analyze this problem. At the same time, it is something that we can really relate to. We dry our hair after wash, and we dry clothes, and in and many such food products that we use, we want to remove moisture. Okay, and so drying is something that is known to civilization for a very long time, even before all the any other mass transfer operation was generated. So it is something very intuitive. Even common people know about this. We know that to dry something, we need sunlight, warm weather, and we live in Chennai. Our humidity goes something about 95, 99 sometimes, especially in monsoon. And if you have ever washed clothes, you will know how difficult it is to dry in a monsoon time. So we know intuitively drying means what, and what it takes to dry faster or slower. This is a very big subject, but for this, as far as this course is concerned, so we are going to touch upon some basic definition of variables, parameters related to drying, and then we will do some simple conceptual understanding only. Okay, so we may not be able to spend time on looking at dryers and design of dryers and so on. Okay, and then the way that we deal with the drying operation is also very different from how we dealt with let's say distillation or absorption or stripping and extraction, so on. Okay, so because mainly this involves gas and solid. This is something you can relate to the previous things, where in distillation we were talking about distillation, absorption we are talking about vapor liquid or a gas liquid systems, and then in extraction we looked at liquid and liquid systems. So this is the first operation we deal with solid. Okay, and solid material can be of many origin, and because of that how it retains moisture and at what rate it relieves is all very complicated subject in the sense. Yes, so you can also have liquid also, but predominantly we will talk about solid gas operations. Okay, so formally we can say drying is basically drying, this is basically removal of moisture from a solid, or it can be also liquid, like he says, by evaporation into a gas stream. So we can kind of think of this as a definition for drying operation. So it involves removal of moisture from either a solid or a liquid. We achieve this removal by evaporating this moisture into a gas stream. Okay, so this is what we are going to use as an operational definition of drying. Now generally this moisture would be of water. Okay, there could be a moisture of other organic liquids also, but generally majority of the cases would be dealing with water moisture, and the gas is typically air. Okay, because air is abundantly available, we can use it for circulation and removal of. Now let us say that I have a solid block and this is wet. Okay, so this is wet solid. Okay, when I say wet, it is basically it contains some amount of water, and we can probably denote that by showing some amount of water. So the blue dots that I see here, show here, is basically water. Now, the water present in solid will exert a vapor pressure. So, the moisture in the wet solid exerts a vapor pressure which we call as PS. Okay, this of course depends on temperature, what temperature we are talking about. Now, let us say that this is actually exposed to a stream of air, and let us say that the air contains some amount of water moisture there itself, equivalent to a equivalent to a partial pressure P bar. Okay, I am using P bar here. So, this is the partial pressure of water. So, we have a water wet solid to some extent, and the water present in the solid will exert a vapor pressure equal to PS. It can be either equal to the bulk water vapor pressure of the corresponding temperature, or it can be lower also. We'll come to that a little later. And then let us say this is exposed to air which also contains some amount of water, and we say that the water content is with respect to the partial pressure P bar. So, we are talking about something like wet towel exposed to ambient air, okay, and the air will contain some moisture related to relative humidity and so on. So, now we look at what are the consequences of this. Okay, so we know that it is a solid and it contains some water, and then it exerts some vapor pressure, and then this is exposed to air which has some partial pressure P bar. Now, depending upon how the P bar and PS these are related, sometimes we see that the moisture can go from the solid to the air, or sometimes the reverse can also happen. Okay, for example, if the vapor pressure exerted by the water in the solid, if that is higher than the partial pressure in the air, now because of thermodynamic reasons, the water will evaporate from the solid into the gas. Evaporation of water from solid to air. This is what we actually mean by drying, and you can see that drying is related to the difference in the vapor pressure exerted by the liquid in the solid and the partial pressure. Okay, and then suppose if the other case, so let us say that we have P bar greater than PS. So, here we are talking about a solid which may have a very little amount of water, and then the corresponding partial pressure can be very small compared to the moisture content in the air. So, in this case, water may condense onto the solid. This is something you must have already felt. You might have dried your clothes, ironed it, put it in your cupboard, and then outside it's raining a lot, and then the relative humidity is very high, and then when you open your cupboard and when you touch your cloth, you will see it's a little bit moist, it's a little bit damp. That's because the dried cloth must have very little amount of moisture, but the outside air contains a lot of moisture. So, moisture can come from the air to the solid also. Okay, so it can also pick up moisture. So, it's a two-way process. The solid can either release moisture, or it can also acquire moisture. It's everything related to what is the relative humidity of the air, what is the partial pressure content in the air, and what is the water content in the solid itself. So, it's related to these two quantities. Now, how long this will go on? Well, we know from thermodynamic consideration that this process of evaporation or condensation will go until the two vapor pressure, the vapor pressure and partial pressures are equal. Then we say mass transfer stops when P bar is equal to PS. I mean, we can think about in terms of fugacity, equivalence of fugacity of the two, but then for all practical purposes we can even relate to the partial pressure and vapor pressure. So, if you want to describe more accurately, you will use fugacities, take into account of the non-ideality and so on. So, when when this condition is established, okay, then there is no more mass transfer, there is no net mass transfer, and then the moisture content at this point, moisture content is called equilibrium moisture content. Equilibrium this equilibrium moisture content is a moisture content when the vapor pressure and the partial pressure are equal, and this moisture is something we usually relate with the symbol X, defined as kilogram of water over kilogram of dry solid. So, moisture is usually expressed in this units of kilogram of water over kilogram of dry solid. Now, this equilibrium moisture content is very much closely related to the composition of the solid material, whether it is inorganic solid or whether it is organic material or whether it is wood or paper. So, let me show you a graph. So, if you look at this figure, what is being plotted is the equilibrium moisture content expressed in the units of kilogram per watt dry solid, and with respect to the relative humidity defined as partial pressure of water vapor over the total pressure. This is basically partial pressure of water divided by the vapor pressure at that particular temperature. Okay, that is the relative saturation or relative humidity. And so you can see that this equilibrium moisture content is plotted for many materials, tobacco leaf, wood, paper, and some inorganic material like zinc oxide. Okay. So what it means is that the amount of water that exists in equilibrium with the air is very much related to the composition of the material itself. And the way that we can understand this this particular plot is by doing a simple experiment, a thought experiment. So let me just connect this. This goes all the way like this. Let's consider the wood as an example. Okay, so I have a small wood log, and let's say initially it contains something close to this point, the moisture content, which is 0.35 kilogram of water by kilogram of dry wood. And let's say I expose this to a air, constant stream of air containing relative saturation of 60%. Okay, so that is this point. So what will happen is that the moisture from the wood block will continue to evaporate into the air, and by the time it comes here, okay, so basically the moisture will move from here to here. Initially it is at 0.35, it loses moisture, because of that the moisture content reduces, okay, and then since this equilibrium moisture content corresponding to 0.6 is somewhere here, the evaporation will continue until the moisture content drops to this value. This is what we mean by this is something like, I don't know, 0.12 or something. So the wood material here would continue to lose moisture until the moisture content drops from 0.35 to 0.12. That is because the equilibrium moisture content curve here shows that when the air is containing 0.6 relative RH, relative humidity, so this is the equilibrium moisture content. Okay, after reaching this 0.12 moisture content, there is no more drying happening. Okay, now let's say if you want to dry even further, then you have to change your air. Suppose if you change the air to 0.2 relative humidity, then you can possibly bring down the moisture to this value, something close to 0.05. By extension, if I use a dry air with no moisture whatsoever, you can probably hope to get completely dried solid also. So this equilibrium moisture content curve is so useful in deciding what should be the drying air quality, up to what humidity you can operate. Okay, so this is where I was talking about in the beginning, how the relative humidity of air controls the rate of drying. Okay, like in Chennai weather, the relative humidity is somewhere here, and let's say if your cloth, if you plot this kind of diagram for cotton, you may have quite a bit of moisture remaining in the cloth or in the cotton cloth. Okay, it's not going to be drying. So that's why you need a dry air to completely dry this solid. Now at this point, we can also distinguish between two kinds of moisture. There is something called bound moisture. So in this example of wood, between 0 to this point, the moisture content over this range, this is called the bound moisture. So moisture up to, so let's say this is point B, is called bound moisture. We can say two things about bound moisture. One is that the vapor pressure exerted by bound moisture will be always less than the vapor pressure of the pure substance, pure water. So vapor pressure exerted by bound moisture will be lesser than that of pure water at the same temperature. As the name implies, bound means this is the water content in the interior of the solid. In the case of wood, so there are cell walls, and there are a porosity. There are small crevices, and there are small capillaries in which the water is content. It's in the inside of the material. Okay, that's what it's called bound moisture. It is not readily available for the evaporation purpose. Okay, and because of its strong association with the interior of the solid, the vapor pressure exerted by this water will be always lesser than that of pure water. So bound water present in the interior of the solid. So in the case of wood, we are talking about water content in the cell walls, capillaries, and absorbed water, and so on. So water content from the 0 to 0.3 in the case of wood would be the bound water, whereas the water content beyond this point B, that we call as an unbound moisture or unbound water. Unbound moisture, or we say unbound water here. So this is moisture content beyond point B. So one of the way you can identify where the bound water and unbound water is by looking at this equilibrium moisture content. Only up to this bound water, there is a dependence of air's relative humidity and the moisture content, and beyond this point B, the moisture content does not depend on the RH of the flowing air. Okay, so that's how you demark this these two. So this is usually this moisture will be on the surface. It forms a nice thin film, on the surface of the solid. this moisture is found as a thin film on the outer surface of the solid, and this water is more like a bulk water, okay, and that's why the vapor pressure will be equal to vapor pressure exerted by unbound water will be equal to that of pure water. So, all these things are we have discussed with respect to wood, but if you take any other material like tobacco here, paper here, you can see that there is a different amounts of bound and unbound water for each case. It is again related to the chemical composition of the solid with which it is made up of. Generally, inorganic material like the zinc oxide would have a very small amount of moisture. You can see that even up to an RH of 0.9, zinc oxide contains very little amount of water. So, basically it's very dry material. Whereas, if you take a vegetable material, organic material like wood and tobacco, cotton, these actually tend to absorb more moisture. Okay, so it's very much characteristic of a solid and its composition. Now, there is another related concept called hysteresis. So, this what I am trying to show here is I am plotting the equilibrium moisture content with respect to the relative humidity of air at equilibrium. The blue curve that you see is the one that I showed before. It's a drying curve. So, you start with the wet solid, expose this to a air of given RH and find the equilibrium moisture content, and let us say you start with this point, and then you replace the air with some other relative humidity, and you basically find this point, and then you can draw this through an experiment. You can nicely trace this drying equilibrium moisture content. Okay. Now, if you reverse the operation, meaning you take a dry bone dry solid with no moisture content to start with, expose this to a moist air with a relative humidity, then then like I said before, the solid will acquire moisture from the air, okay, by reabsorption. It's called regain. So, you will see that the red curve, ideally it should follow the blue curve, but there is always a difference between the drying and condensation curve. This is what we call it as a hysteresis. The hysteresis is something related to how we are not able to reach equilibrium in both ways. Okay. So, like I said, ideally we want to follow the same blue curve, but in practical experiments you will see there is always a small gap between the drying curve and condensation curve. And so, what is the physical significance or practical significance of this this curve is that let's say you dry something, and then you dry it, and then if you re-expose to air with a higher moisture content, the solid will acquire more moisture. So, if you want to preserve the water content in a material, you need to pack it. You need to pack it such a way that it cannot be exposed again with water with higher humidity. Okay. So, this is related to how to preserve a dry material in dry state. So, if you have ever not ever, everybody eats potato chips, right, and you see that it is nicely packed with the puffed air. Okay. So, that if you look at the packing that you have, it is actually multi-layer laminated packaging, so that water, moisture cannot really enter. If it enters, you won't really enjoy the crispness of the chips. So, it's very important that after you dry, how you preserve that dried material. You can't just keep it simply open, it will acquire more moisture. So, this drying and absorption is actually a kind of both way process. Okay, a material can release moisture, it can also absorb moisture. So that's what this hysteresis or this reabsorption means. Okay, so drying and then preserving the dried material is equally important. Okay, so in the packaging industry, this moisture barrier is a quantity that is measured to see how much moisture you can actually stop coming into the product, especially food packaging and snack and biscuits and so on. All right. So now with all this introduction, now I would like to actually formally define certain variables, quantities that we will be using in this process. Generally, so terminologies. So we talk about moisture content, wet basis. With regard to other mass transfer operation, we talked about partial pressure, concentrations, mole fractions, mole ratios, etc., etc. With regard to the drying, we use what is called this moisture content on wet basis. We use a small x for this. This is defined as kg of water over kg of wet solid. So when I say wet solid, it means the weight of the dry solid plus the amount of moisture content in it. So kg of water by kg of water plus kg of solid. This is what this kilogram of wet solid means. Now this can also be written differently, kg of water over kg of dry solid. So let me write this as dry solid. Dry solid. I already introduced a moisture content in terms of kilogram of water by kilogram of dry solid. So that we call capital X. So this small x, which is moisture content in wet basis, is related to moisture content in dry basis. Okay, so the moisture content in dry basis is capital X, defined as kilogram of water by kilogram of dry solid. And then there is something called equilibrium moisture content. And we use symbol X star here. So this is the moisture content of a solid in equilibrium with a gas of a given partial pressure or RH. Note that this equilibrium moisture content is not a fixed quantity. It is a quantity that depends on what is the partial pressure of the exposed gas is. Okay, that's what these diagrams were referring to. By changing the relative humidity of the exposed air, I can control the equilibrium moisture content. Okay, so it is very much dependent on the quality of the drying air, the quality of the material, temperature, and so on. So it's not a fixed quantity. Then bound moisture. So this is something I already discussed. This is the moisture content of a solid that exerts vapor pressure less than that of pure water. Okay, we don't have any symbol for that. And then we have this unbound moisture. So this is the moisture content of a solid that exerts a vapor pressure equal to that of pure water at the same temperature. Here also we can add there is something called free moisture. So this is nothing but x minus x star. This is the moisture available for removal. So this is the equilibrium moisture content of a typical characteristic system. So here we have 0 and this is x bar. So here this moisture content from here onwards, this is the unbound moisture. This is unbound moisture, and over this range, this is the bound moisture. And if I take any particular RH value, there is a corresponding equilibrium moisture corresponding to this RH. So this is the equilibrium moisture content. And the free moisture is, suppose if I have some x here, so this would be the free moisture. X minus x star is something that is available for drying, and the material would have some amount of moisture corresponding to equilibrium moisture that cannot be removed with this air. Okay, and this free moisture and equilibrium moisture is very much dependent on RH. Suppose if we take a air somewhere here, the equilibrium moisture now becomes smaller and the free moisture becomes larger. Okay, so that's how we understand these things. Now, as far as the drying operation is concerned, there are batch drying and there are continuous drying. In the batch drying, a wet solid is kept stationary and a stream of air is flown past it continuously. Okay, So that's the batch drying. So batch with respect to the solid. Solid is not moving. Solid is stationary. Only the drying air is passed over. Whereas in the continuous drying, both solid and the drying air, both of them will be flowing from one end to the other end of the equipment, whatever that configuration is. And the drying equipment called a dryer or dryer, like this, both spellings are used. So this the design of this dryer depends on whether we are talking about batch drying or continuous drying, and what is the nature of heating. Are we doing a direct heating, or we are going to do indirect heating? Those are all the quantities that we should think about. And also it depends on what is the material that we are drying. Are we drying a liquid material? Are we drying a solid material? If it's a solid material, is it inorganic material, or is it more flexible paper like soft material? So so nature of the solid that we want to dry also will dictate what dryer to be used. Okay. And industrial dryer, these are some of the things that I want to just quickly pass through because we won't be able to discuss this in detail. So there are dryers called tray dryers, through circulation dryers, vacuum shelf dryers, rotary dryers, tunnel dryers, and then there are so many kind of them. So if you especially look at Perry's handbook, you will see that a nice diagram of many kinds of this dryer and what material they are useful for. Okay, so if you look at you know, this drying of food products like this chips and biscuits, bakery items. Okay, so mostly the tray dryers are used, okay, in a continuous mode or in a batch mode. And more larger industrial scale applications involving drying of pasty material or you know, granular materials requires maybe fluidized beds and rotary dryers and so on. So, okay, so it's a very big field, and like I said before, we will not be able to discuss this design of dryers. Is something that, you know, if you're interested, you can refer to textbook or the Perry's handbook for more information. What I will do in this course is that in the next class, I'll talk about what are the elements of drying kinetics, batch drying kinetics, and what we can infer from such drying batch kinetics. Okay, more from a conceptual point of view rather than a design point of view. Okay, so I'll stop here and we'll meet on Friday.